For millions of years, the Earth was ruled by creatures of unimaginable size and strength. Among them, some stood out not just because of their physical power, but because of their lethal capabilities. These were the most dangerous dinosaurs ever discovered, apex predators that dominated their ecosystems, left behind fossilized traces of their hunts, and continue to fascinate scientists and the public alike. But what exactly makes a dinosaur dangerous? Is it size, speed, intelligence, or is it a perfect blend of anatomical and behavioral traits that gave them an edge in the struggle for survival? Danger in the prehistoric world was not a simple concept. A dinosaur's ability to kill did not always depend on brute force. It could come from cunning ambush tactics, specialized teeth designed to crush bone, claws capable of slicing through flesh, or even behavior like group hunting. The fossil record has offered glimpses into these features, providing scientists with valuable evidence to understand which species were true apex predators. Paleontology, the study of ancient life through fossils, has been instrumental in piecing together this puzzle. Every new fossil site adds another fragment to the vast and incomplete story of life on Earth. It begins with the careful excavation of bones buried under layers of sediment, often in harsh and remote environments. The work is slow, precise, and often uncertain. What starts as a small fragment, perhaps a tooth, a claw, or a vertebrae, can lead to the identification of an entirely new species or reveal surprising traits in a known one. Dangerous dinosaurs are typically recognized through a combination of skeletal features. Large skulls with powerful jaw muscles, serrated teeth for slicing meat, strong hind limbs built for running or pouncing, and claws adapted for gripping or killing prey are among the most telling signs. But not all danger is visible in bone. Sometimes fossilized trackways suggest behavior. A series of prints showing coordinated movement may hint at pack hunting. Healed injuries on prey species suggest repeated predation. Even coprolites, fossilized feces, can provide insight into diet and digestive power. One of the most iconic predators, Tyrannosaurus rex, is a classic example. With a skull over 5 feet long and teeth that could crush bone, it exemplifies what scientists refer to as hypercarnivory. But it was not alone. Across different continents, in various periods of the Mesozoic era, other predators evolved to fill similar ecological roles. From the river-stalking Spinosaurus to the swift and intelligent Utahraptor, nature repeatedly produced deadly hunters, each uniquely adapted to their environment. Fossil evidence often raises as many questions as it answers. In some cases, the remains of two species are found close together, one clearly having preyed upon the other. Tooth marks on bones, embedded teeth left behind during a kill, or even fossilized gut contents give paleontologists rare confirmation of predator-prey interactions. Yet many hypotheses must be drawn from comparative anatomy and modern analogues studying living animals like crocodiles, birds, and big cats to infer the behavior of extinct species. Geological context is also key. Sedimentary layers can tell scientists whether a dinosaur lived in a forest, floodplain, desert, or coastal region. Each habitat shaped the form and function of its dominant predators. In coastal North Africa, Spinosaurus evolved long, narrow jaws suited for catching fish. In the open plains of what is now Argentina, Giganotosaurus developed massive jaws and muscular frames to take down giant sauropods. These details, when carefully analyzed, help identify the most dangerous predators of each region and era. Danger is not always a measure of size. Smaller dinosaurs like Deinonychus or Troodon may have lacked the brute force of giants like T. Rex, but their agility, speed, and possibly high intelligence made them formidable. They may have hunted in packs, coordinated attacks, or used stealth and ambush to overcome prey larger than themselves. Fossilized evidence of claw marks, joint dislocations in prey, and strategic bite locations all suggest complex hunting strategies far beyond what size alone might imply. Scientific interpretation is always evolving. As new discoveries are made and technologies improve, our understanding of dinosaur behavior and physiology deepens. High-resolution scans of skulls allow researchers to model bite forces. Biomechanical analysis simulates movement, revealing how fast or agile a species may have been. Isotope analysis can show whether a dinosaur was a coastal or inland dweller, while wear patterns on teeth indicate the type of food consumed. Every new method refines our ability to determine which dinosaurs were truly dangerous. More recently, advancements in digital modeling and artificial intelligence have helped paleontologists reconstruct entire ecosystems in virtual space. By placing known species into accurate geographic and temporal contexts, researchers can simulate interactions between predators and prey. This allows for deeper insight into dominance hierarchies, niche partitioning, and the evolutionary arms race that drove some species toward lethal specialization. Such reconstructions have shown, for example, how different predatory dinosaurs might have avoided direct competition by focusing on different prey or hunting strategies. Public fascination with deadly dinosaurs is not new. Popular media often portrays these animals as monsters, exaggerating their danger for dramatic effect. But the scientific reality is far more complex and far more interesting. These were not mindless killing machines, but organisms shaped by millions of years of evolution, each finely tuned to survive in a specific time and place. Understanding their danger through a scientific lens allows us to appreciate not just their power, but their place in the broader tapestry of life on Earth. Behind every fossil lies a story of life, death, and survival in a world vastly different from our own. When scientists uncover the remains of a powerful predator, they don't just see bones. They see evidence of a struggle for dominance, an adaptation for survival, and a glimpse into a lost world where danger was a daily reality. This documentary aims to explore that world, dinosaur by dinosaur, through the lens of discovery and science. We will journey through the fossil record to uncover the most dangerous dinosaurs ever discovered. From the well-known giants to the lesser-known assassins of the ancient world, each chapter will bring to life the evidence that marks these creatures as apex predators. With each step, we will rely on hard data bones, teeth, trackways, and more to separate myth from reality and show what truly made these dinosaurs the deadliest beings to ever walk the planet. When people think of dinosaurs, one name often stands above all others: Tyrannosaurus rex. Towering over its environment with a powerful build, immense skull, and bone-crushing bite, Tyrannosaurus rex has long been portrayed as the ultimate prehistoric predator. But beyond the legends and dramatizations lies a wealth of scientific data that paints a more precise and astonishing picture of this apex hunter. From fossilized bones to advanced biomechanical studies, Tyrannosaurus rex continues to reveal itself not just as a creature of terror, but as a pinnacle of evolutionary design in the world of Mesozoic predators. Tyrannosaurus rex lived during the late Cretaceous period, approximately 68 to 66 million years ago. Its fossil remains have been found predominantly in what is now North America, in areas once rich with river systems, floodplains, and dense vegetation. The environment was teeming with life-large herbivores like Triceratops, Edmontosaurus, and Ankylosaurus, which provided abundant prey. Standing up to 40 feet long and weighing around 9 tons, Tyrannosaurus rex was among the largest land carnivores to ever exist. One of the defining features of Tyrannosaurus rex was its skull. Measuring over 5 feet in length, it housed some of the strongest jaw muscles ever recorded in the fossil record. Estimates suggest that its bite force could exceed 12,000 pounds, enough to shatter bone with ease. This force wasn't just theoretical, it's supported by fossil evidence. Bones of prey species, including Triceratops and Hadrosaurs, have been discovered with deep puncture marks and shattered sections, consistent with a Tyrannosaurus rex attack. In some cases, broken bones even show signs of healing, suggesting that the victim survived the initial encounter. Its teeth were uniquely suited for delivering damage. Unlike the blade-like teeth of some theropods, the teeth of Tyrannosaurus rex were thick, conical, and serrated, designed not to slice cleanly, but to crush and tear. Some teeth measured over 12 inches long when including the root. They were spaced in such a way that they could distribute force effectively, and each tooth was continuously replaced over time. Fossilized dung, or coprolites, attributed to Tyrannosaurus rex have been found to contain fragments of bone, confirming its ability to consume and digest hard materials. Despite its enormous head, Tyrannosaurus rex had relatively small arms, a feature that has puzzled scientists and sparked much debate. Although tiny in proportion, these arms were heavily muscled and featured large claws. They may have played a role in holding onto prey or assisting in mating, but it is clear that they were not the primary tools of attack. That role was filled entirely by the skull and jaws. In this sense, Tyrannosaurus rex was a head-dominated predator, an evolutionary design that focused almost all offensive capability into a single devastating weapon. Its sense of smell was exceptionally well developed. Studies of fossilized skulls show large olfactory bulbs and nerves, indicating that Tyrannosaurus rex had a keen sense of smell, likely used for tracking prey over long distances or locating carcasses. This raises the long-standing question, was Tyrannosaurus rex purely a hunter, or did it also scavenge? Modern understanding supports both. While Tyrannosaurus rex was certainly capable of bringing down live prey, it would have taken advantage of carrion when the opportunity arose, just as today's lions and wolves do. In the harsh Cretaceous ecosystem, energy conservation could mean the difference between life and death. Mobility was another key trait. While Tyrannosaurus rex was not built for extreme speed, its powerful hind limbs suggest it could reach moderate speeds sufficient for ambush or short pursuits. Recent biomechanical models estimate its top speed between 12 and 20 miles per hour, depending on body mass assumptions. More importantly, Tyrannosaurus rex had an efficient stride that allowed it to cover ground steadily, and its long tail served as a counterbalance, aiding in maneuverability. One of the most compelling pieces of evidence for its role as a dominant predator comes from trace fossils. Trackways preserved in sediment show Tyrannosaurus rex moving through its environment, sometimes alone, sometimes possibly with others. Although the idea of pack behavior in Tyrannosaurus rex remains controversial, some fossil sites suggest that multiple individuals may have fed together on large carcasses. This social dimension, if confirmed, would further elevate its status as a complex and dangerous species. Juvenile Tyrannosaurus rexes provide additional insight. They were more slender and agile than adults, with relatively longer legs. This suggests a shift in hunting strategy as they matured, perhaps targeting smaller, faster prey in youth and moving to larger, slower herbivores in adulthood. This life stage transition also reduced competition between age groups, allowing the species to dominate multiple niches across its lifespan. The fossil record offers many iconic specimens. Sue, one of the most complete Tyrannosaurus rex skeletons ever found, measures over 40 feet in length and provides detailed information about the species' anatomy. Pathologies on Sue's bones indicate injuries and infections, telling a story of a hard life in a dangerous world. Another specimen, known as Stan, revealed details about muscle attachment and bite mechanics, furthering our understanding of how Tyrannosaurus rex functioned as a living predator. Yet Tyrannosaurus rex was not without its challenges. Despite its power, it lived in an ecosystem with other dangerous species and faced threats from disease, injury, and starvation. Fossil evidence shows that even the king of the dinosaurs bore the scars of survival. Healed bone fractures, signs of infection, and even bite marks from other Tyrannosaurus rexes suggest that intraspecific conflict was common. Territorial disputes, competition for mates, or fights over food could turn these massive predators against each other. The extinction of Tyrannosaurus rex came suddenly, around 66 million years ago, as part of the mass extinction event likely triggered by an asteroid impact near the present-day Yucatan Peninsula. This event marked the end of the Cretaceous period and wiped out approximately 75% of all species on Earth. Tyrannosaurus rex, like many other dinosaurs, disappeared from the fossil record after this point, leaving behind only bones and clues. Yet, its legacy endures. As new specimens are discovered and technologies advance, our understanding of Tyrannosaurus rex continues to evolve. From bite force simulations to 3D reconstructions of its musculature, scientists are uncovering not only how it hunted, but how it lived, moved, and interacted with its environment. It remains a symbol of prehistoric power, not just because of its size, but because of the scientific depth with which we can study it. In the search for the most dangerous dinosaurs, Tyrannosaurus rex stands not just as a titan of its time, but as a benchmark by which other predators are measured. Its anatomy, behavior, and ecological dominance make it one of the best understood apex predators in the fossil record. While other dinosaurs may have been larger, faster, or more unusual, few combined so many lethal traits into one terrifying whole. In the story of prehistoric danger, Tyrannosaurus rex remains a central figure, fearsome, fascinating, and forever iconic. In the vast prehistoric landscapes of what is now North Africa, a predator once roamed that defied the standard image of a land-based killer. This creature, known as Spinosaurus aegyptiacus, was unlike any other dinosaur. Towering and elongated, with a sail-like structure on its back and adaptations that suggest a semi-aquatic lifestyle, Spinosaurus has become one of the most enigmatic and controversial predators ever discovered. Its fossils, found primarily in the Kem beds of Morocco, reveal a story not of dominance on dry land, but of mastery over rivers, swamps, and ancient deltas. Spinosaurus lived during the mid-Cretaceous period, around 100 to 95 million years ago. Its environment was a lush, humid ecosystem dominated by braided rivers, dense forests, and abundant aquatic life. Fish, crocodile-like reptiles, and other large aquatic prey filled the waters, while on land, massive herbivores and theropods roamed. In this complex food web, Spinosaurus stood apart. It was not built for pursuit on the plains, but for ambush beneath the water's surface. Estimates of its size have evolved with new discoveries, but current reconstructions suggest that Spinosaurus could grow up to 59 feet in length, making it possibly the longest known theropod. It had a long, narrow skull filled with conical teeth, perfect for gripping slippery prey. Unlike the serrated, blade-like teeth of many land predators, these teeth showed little evidence of cutting flesh. Instead, they were designed to puncture and hold, much like the teeth of modern crocodilians. This dental adaptation, combined with a long snout and raised nostrils, supports the hypothesis that Spinosaurus primarily hunted aquatic prey. Its skull was also equipped with pressure-sensitive receptors structures seen in crocodiles that allow them to detect movement in water. This would have given Spinosaurus an advantage when stalking prey beneath the surface, allowing it to remain submerged with only its snout exposed while waiting for the perfect moment to strike. Fossilized jawbones show evidence of these receptors, further linking its behavior to that of modern aquatic hunters. Its limbs also tell a unique story. The forelimbs were powerful and featured large claws, likely useful for grappling with prey or navigating through vegetation. The hind limbs, however, were shorter and more compact than those of other giant theropods. This shortening, along with a more flexible pelvis, suggests that Spinosaurus was not built for long-distance running, but for paddling and wading. Its long, muscular tail, once thought to be inflexible, is now believed to have been a major propulsive force. Recent fossil discoveries have revealed that the tail had tall neural spines and was flattened laterally, resembling the tails of modern aquatic animals like newts and crocodiles. This tail, when combined with webbed feet and other aquatic features, supports the idea that Spinosaurus was an excellent swimmer. It likely hunted in rivers and lakes, using stealth and sudden bursts of speed to capture fish and other aquatic animals. Isotopic analysis of its bones also supports this aquatic lifestyle. The chemical composition of its fossils suggests that it spent a significant portion of its time in water, much more than its theropod relatives. The most striking feature of Spinosaurus is its sail. This structure, composed of elongated neural spines extending from its vertebrae, rose several feet above its back. Its purpose remains one of paleontology's greatest mysteries. Some scientists believe it was used for display, either to attract mates or intimidate rivals. Others suggest it played a role in thermoregulation, helping the animal absorb or dissipate heat. A more recent theory proposes that the sail may have helped with stability while swimming, acting like a keel or fin to aid in maneuverability. Whatever its true function, the sail added to the creature's distinctive profile and may have played multiple roles throughout its life. Despite its aquatic adaptations, Spinosaurus still interacted with the terrestrial world. Fossil evidence shows that it shared its ecosystem with other large predators, including Carnotaurus and Deltadromeus. These interactions were likely complex. Spinosaurus may have avoided direct competition by focusing on aquatic prey while its rivals hunted land-dwelling herbivores. Such niche partitioning would have allowed multiple apex predators to coexist in the same region without exhausting shared resources. One of the challenges in understanding Spinosaurus has been the fragmented and scattered nature of its fossils. The original specimen discovered in Egypt in the early 20th century was destroyed during World War IE. For decades, scientists relied on sketches and photographs until new discoveries emerged in Morocco. These newer finds have reshaped our understanding of the creature, challenging long-held assumptions and prompting debates among paleontologists. As more specimens are uncovered, the picture continues to evolve, revealing a creature more specialized and complex than previously imagined. The biomechanics of Spinosaurus have also been a subject of intense study. Computer models and simulations have tested its buoyancy, swimming ability, and structural strength. While some researchers argue that it may have struggled to dive deeply due to its hollow bones, others believe it floated just beneath the surface, using subtle tail and limb movements to move quietly through the water. It may have relied on a strategy similar to that of a modern heron, stalking and spearing fish with quick, decisive strikes. Its diet, supported by both dental analysis and stomach contents found in related species, likely included a range of fish species, including large coelacanths and sawfish. The abundance of fish fossils in the same strata as Spinosaurus supports this. In one case, a fossilized spinosaurid tooth was found embedded in a pterosaur bone, suggesting occasional opportunistic feeding. But overwhelmingly, the evidence points to a life built around the water, where prey was plentiful and competition with terrestrial hunters could be minimized. The extinction of Spinosaurus occurred well before the end Cretaceous event that wiped out T. rex, and other North American dinosaurs. Shifts in climate, sea levels, and ecosystem dynamics likely played a role. As rivers changed course and wetlands disappeared, the specialized adaptations that once gave Spinosaurus an edge may have become its downfall. Its reliance on aquatic habitats would have made it vulnerable to environmental changes that affected its food sources and breeding grounds. Yet, its legacy is a powerful one. Spinosaurus stands as a testament to the diversity of dinosaur life and the range of evolutionary experiments that played out during the Mesozoic era. It was not simply a terrestrial predator modified for water, but a true hybrid, a dinosaur that bridged the gap between land and sea. In a world dominated by giants, it chose a different path, evolving into a master of the aquatic realm. The story of Spinosaurus continues to unfold. Each new fossil challenges our assumptions and adds to the narrative of a creature that defied classification. It forces scientists to rethink what it means to be a dinosaur and expands the boundaries of what was possible in prehistoric ecosystems. Among the pantheon of deadly dinosaurs, Spinosaurus remains one of the most remarkable, not just for its size or power, but for the unique way it lived, hunted, and thrived in a world of water. In the heart of what is now Patagonia, Argentina, during the late Cretaceous period, a predator emerged that would rival the most iconic of carnivores. Towering and agile, this beast was known as Giganotosaurus carolinii. It lived approximately 98 million years ago, during an age when South America was a continent of titanic creatures and ferocious competition. Giganotosaurus, whose name means giant southern lizard, was a true apex predator, designed not only for power, but also for strategic hunting in packs or solitary ambush. The fossilized remains of Giganotosaurus were first unearthed in 1993 by an amateur fossil hunter named Rub N. Dario Carolini, leading to one of the most significant paleontological discoveries of the 20th century. The specimen, remarkably complete for such a large theropod, revealed a dinosaur that was comparable in size to Tyrannosaurus rex, measuring up to 43 feet in length and weighing over 8 tons. But unlike T. rex, which was heavily built with a crushing bite, Giganotosaurus was leaner, faster, and adapted for slashing attacks. Its skull, over 5.5 feet long, was narrow and elongated, filled with sharp, blade-like teeth. These serrated weapons were ideal for slicing through flesh rather than crushing bone. Its jaws were strong, but not as forceful as those of Tyrannosaurus. Instead, Giganotosaurus relied on speed and technique, using rapid strikes to weaken its prey through blood loss and tissue damage. The design of its skull with large fenestrae to reduce weight and powerful jaw muscles enabled repeated biting without the need for a singular, bone-crushing force. Giganotosaurus belonged to a group of theropods known as Carcharodontosaurids, which included other massive predators such as Carcharodontosaurus and Mapusaurus. These dinosaurs were characterized by their size, agility, and deadly dentition. In South America, Giganotosaurus reigned supreme in a landscape teeming with colossal herbivores. Among its potential prey were enormous sauropods such as Argentinosaurus, one of the largest land animals to ever walk the earth. These titans could reach lengths of over 100 feet, making them formidable targets for any predator. Yet Giganotosaurus was not deterred by size. It may have hunted cooperatively, a behavior suggested by fossil evidence of closely related species found in group assemblages. Though direct proof of pack hunting remains debated, the possibility opens a window into a more complex social structure among large theropods. Coordinated attacks would have allowed Giganotosaurus to take down prey far larger than itself, using tactics that combined agility, communication, and brute strength. Its limbs supported this predatory lifestyle. The hind legs were muscular and adapted for running, giving it an estimated top speed of up to 31 miles per hour, remarkably fast for such a massive creature. The forelimbs, while not as reduced as those of Tyrannosaurus, were still relatively short but strong, with 3-fingered hands that may have assisted in grasping or stabilizing struggling prey. Its tail was long and rigid, providing balance and counterweight during high-speed chases or during powerful lunges. The brain of Giganotosaurus, studied through endocasts of its cranial cavity, was modest in size but specialized. It had well-developed olfactory bulbs, indicating a keen sense of smell. This would have been vital for tracking prey across long distances or detecting carcasses. Its vision was forward-facing but less stereoscopic than that of T. rex, suggesting it may have relied more on movement and scent than depth perception in the final stages of a hunt. Its environment was no less dramatic. The Cretaceous Patagonian landscape was a mix of floodplains, forests, and river systems. The region supported a vast array of herbivores, from sauropods to ornithopods, providing ample food sources, but competition was fierce. Giganotosaurus may have shared its domain with other theropods and dangerous crocodile-like predators. Territorial disputes and intraspecific conflict could have been as perilous as any hunt, with fossil evidence hinting at healed injuries and possible bite marks from other large carnivores. Despite its dominance, the reign of Giganotosaurus was not eternal. Environmental shifts, changing ecosystems, and the rise of new competitors likely played roles in its eventual disappearance. The fossil record remains incomplete, leaving gaps in the story of how this predator lived and died. Yet, its discovery was a turning point, reshaping our understanding of predatory dinosaurs outside of North America and challenging the long-held belief that Tyrannosaurus was the unrivaled king of the carnivores. Giganotosaurus became a symbol of the evolutionary arms race that unfolded in isolation on the southern continents. While North America saw the rise of tyrannosaurs, South America developed its own line of monstrous killers, lighter, faster, and more specialized. This divergence underscores the incredible adaptability of dinosaurs and the role of geographic separation in shaping life's trajectory. Each continent became a canvas for natural selection, producing apex predators tailored to their environments. Today, Giganotosaurus is remembered not just for its size, but for what it represents: a counterpoint to the tyrant king, a creature that thrived through speed, cooperation, and finesse. In the ever-evolving story of dinosaur evolution, it stands as a reminder that power comes in many forms and that survival often depends not on brute force alone, but on strategy, specialization, and adaptation. Among the most dangerous dinosaurs ever discovered, Giganotosaurus holds its place not through legend, but through evidence, fossils that speak of an animal engineered by nature for lethal precision. It is a hunter born of its time and place, a reflection of the Cretaceous world in the southern hemisphere, and a true giant of deep time. During the early Cretaceous period, approximately 125 million years ago, the land that would one day become the American West was a vastly different place. Dense forests stretched across broad floodplains, rivers carved winding paths through the terrain, and a diverse array of plants and animals thrived in a warm, humid climate. In this dynamic ecosystem lived one of the most formidable predators ever discovered, Utahraptor ostromysorum. Its fossils were first found in the early 1990s in Utah, and this discovery sent ripples through the paleontological community. It challenged long-standing assumptions about the size and capabilities of dromaeosaurid dinosaurs, revealing a predator unlike any other in its family, a superraptor built for power, speed, and deadly precision. Utahraptor belonged to the Dromaeosauridae family, a group of small to medium-sized feathered theropods commonly referred to as raptors. These dinosaurs were known for their agility, intelligence, and distinctive sickle-shaped claws on the second toe. However, Utahraptor was an outlier in this group, surpassing its relatives by a significant margin in both size and ferocity. While the famous Velociraptor was roughly 6 feet long and weighed less than 100 pounds, Utahraptor was an apex predator, measuring up to 23 feet in length and weighing nearly 1,000 pounds, a giant among raptors. This immense size did not come at the cost of agility or speed. Utahraptor's anatomy reveals a creature built for swift movement and powerful strikes. Its hind limbs were long and muscular, ending in feet armed with the iconic sickle claws. These claws could grow to over 9 inches in length, curved and razor-sharp, perfectly adapted for slashing through the flesh of prey. Fossilized remains show evidence that these claws were kept sharp by retracting them off the ground, a trait that preserved their deadly edge and enhanced their effectiveness in hunting. The hunting strategy of Utahraptor likely combined its physical prowess with advanced intelligence. Studies of related dromaeosaurids suggest that these dinosaurs had relatively large brains for their size, with well-developed areas dedicated to coordination, balance, and sensory processing. While direct evidence of Utahraptor's intelligence remains limited, its close relatives demonstrated complex behaviors, including pack hunting, parental care, and possibly coordinated attacks. It is plausible that Utahraptor, with its greater size and capabilities, exhibited similar or even more advanced social behaviors, hunting in groups to take down larger prey or using ambush tactics to surprise and overpower targets. The skull of Utahraptor was elongated and narrow, equipped with sharp, serrated teeth that were ideal for slicing through muscle and tendons. Unlike larger theropods that relied on brute force and crushing bites, Utahraptor's teeth were adapted for precision strikes. Combined with its sickle claws, it could inflict multiple deep wounds quickly, weakening prey through blood loss and shock. This hunting method would have been effective against a variety of prey species, including early herbivorous dinosaurs such as iguanodontids, which roamed the same environment. Utahraptor's discovery in the early 1990s came at a time when the fossil record for large dromaeosaurids was sparse. Its fossils were found in the Cedar Mountain Formation of Utah, a geological formation known for preserving a rich array of Cretaceous life. The fossils included parts of the skeleton such as vertebrae, limb bones, and the distinctive sickle claws, providing paleontologists with the evidence needed to reconstruct this giant predator. The species name Ostrom mysorum honors John H. Ostrom and Warren A. Mays, two key figures in the study of dromaeosaurids and dinosaur paleontology. The ecosystem in which Utahraptor lived was diverse and competitive. The early Cretaceous period saw a proliferation of plant-eating dinosaurs, creating a rich food source for carnivores. Iguanodontids, early ceratopsians, and various sauropods shared this landscape, each filling different ecological niches. The presence of Utahraptor added a crucial predator-prey dynamic, influencing the behavior and evolution of herbivorous dinosaurs. The threat posed by such a large and agile hunter would have shaped the defensive strategies of its prey, driving evolutionary arms races that increased the complexity of Cretaceous ecosystems. Although Utahraptor's fossils are less numerous compared to some other dinosaurs, ongoing discoveries continue to provide insight into its life history and behavior. Comparisons with better-known relatives such as Deinonychus and Velociraptor suggest that Utahraptor likely exhibited feathers, which could have served multiple functions, including insulation, display, and aiding in balance and maneuverability during hunting. These feathers, though not adapted for flight, were an important evolutionary feature that links dinosaurs like Utahraptor to modern birds. The physical adaptations of Utahraptor extended beyond its claws and teeth. Its forelimbs were robust and equipped with three-fingered hands ending in sharp claws. These limbs may have been used to grasp prey tightly, hold struggling animals, or even assist in climbing or balance during combat. The tail was long and stiffened by elongated vertebral processes, acting as a counterbalance to the body and enabling quick, agile movements during high-speed chases or sudden attacks. In terms of sensory capabilities, Utahraptor likely possessed keen vision and an acute sense of smell. The size and shape of its skull suggest large eye sockets, indicating good eyesight necessary for spotting prey at a distance. Its olfactory bulbs, responsible for detecting odors, were also well developed, allowing it to track prey or carrion efficiently. These sensory adaptations, combined with its physical attributes, made Utahraptor a formidable hunter capable of exploiting a variety of hunting strategies. The discovery of Utahraptor also raised important questions about the evolutionary pathways of dromaeosaurids. Previously, these dinosaurs were thought to be relatively small predators limited in size and prey range. Utahraptor's existence demonstrated that this group evolved a range of sizes and hunting styles, from small pack hunters to large solitary predators. This diversity highlights the adaptability of theropods and the complex ecological roles they played during the Cretaceous. Paleontologists continue to debate the social behavior of Utahraptor. While direct fossil evidence of pack hunting remains scarce, trackways and fossil sites containing multiple individuals of related species suggest the possibility of group behavior. If Utahraptor hunted in packs, it would have been capable of taking down larger and more dangerous prey than a solitary hunter could manage, increasing its dominance in the ecosystem. Alternatively, it may have been a solitary ambush predator, relying on stealth and surprise rather than strength in numbers. The extinction of Utahraptor, like many other dinosaurs, was likely influenced by environmental changes and shifts in ecosystem dynamics during the Cretaceous period. Volcanic activity, climate fluctuations, and the rise of new dinosaur groups may have contributed to its decline. Despite its disappearance, Utahraptor remains a symbol of evolutionary success and complexity, offering a glimpse into the incredible diversity of predatory dinosaurs. In conclusion, Utahraptor stands as one of the most dangerous and fascinating dinosaurs ever discovered. Its combination of size, strength, agility, and intelligence marks it as a superraptor, a predator that challenged the boundaries of what was thought possible for dromaeosaurids. Its fossils continue to provide valuable insights into dinosaur evolution, behavior, and ecology, enriching our understanding of the Cretaceous world. This giant raptor reminds us that the prehistoric past was full of surprises, with creatures evolving unique adaptations to survive and dominate their environments. Utahraptor's legacy is a testament to the power of natural selection and the endless creativity of life through deep time. In the late Cretaceous period, around 72 to 69 million years ago, the southern continents held a unique and diverse assembly of dinosaurs. Among these, a predator emerged that combined speed, agility, and terrifying appearance to dominate its environment, Carnotaurus sustre. This dinosaur, whose name means meat-eating bull, was first discovered in 1984 in Patagonia, Argentina, and instantly captured the imagination of paleontologists and the public alike. Its unusual features and adaptations make it one of the most fascinating and dangerous carnivores of the Cretaceous. A true speed demon equipped with horns that resemble those of a modern-day bull. The fossilized remains of Carnotaurus were found in the La Leona Formation, a rich sedimentary layer preserving a window into the late Cretaceous ecosystem of South America. The discovery was extraordinary not only because of the skeleton's exceptional preservation, but also due to its unique anatomy. Carnotaurus stands out among theropods with its lightweight build, distinct bull-like horns above its eyes, and unusually small forelimbs, even smaller than those of the infamous Tyrannosaurus rex. Unlike many other large carnivores that relied primarily on brute strength and heavy bone structure, Carnotaurus was built for speed and swift ambush hunting. It measured approximately 29 feet in length and weighed around 1.3 tons, making it a medium-sized theropod, but one optimized for rapid movement. Its long, slender legs with well-developed muscles suggest it could run at impressive speeds, perhaps rivaling some modern-day large predators. This speed was a crucial adaptation in an environment filled with fast-moving herbivores that required efficient and agile hunting techniques. The defining feature of Carnotaurus is its pair of thick, bony horns protruding above the eyes, each shaped like a bull's horn. These horns were likely used for intraspecific combat, signaling dominance or intimidation. Some scientists propose that Carnotaurus may have engaged in headbutting contests with rivals, similar to modern animals like goats or bison. These horns could also have been a display feature to attract mates or warn competitors, adding a social dimension to this dinosaur's behavior. Carnotaurus's skull was low and narrow, with sharp teeth adapted for slicing through flesh. Its jaw structure and bite force were not as powerful as some larger theropods, indicating that it relied more on quick strikes and speed rather than crushing bites. Combined with its keen senses, Carnotaurus was likely a swift and deadly ambush predator, using surprise and agility to capture prey before it could escape. Its forelimbs were notably reduced, with tiny, stubby arms that ended in 4 fingers, each tipped with small claws. Unlike other theropods that use their arms for grasping or fighting, Carnotaurus's limbs seem to have been nearly useless in prey capture. This reduction suggests a shift in hunting strategy, focusing instead on the powerful hind limbs and jaws for offense. The loss of functional arms might also have reduced weight and improved balance, aiding in speed and maneuverability. Carnotaurus's tail was muscular and flexible, providing balance and agility during rapid pursuits. Its vertebrae had specialized structures that allowed strong muscle attachments, which likely helped stabilize the tail as a counterbalance to the front of the body. This anatomical feature was essential for sharp turns and sudden bursts of speed, enabling Carnotaurus to keep up with fast-moving prey across varied terrain. The environment Carnotaurus inhabited was rich in herbivorous dinosaurs, such as hadrosaurs, titanosaurs, and small ornithopods. These animals were often large and well-defended, requiring predators to be both fast and tactical. Carnotaurus's adaptations suggest it hunted these herbivores through ambush tactics, using cover to approach silently before launching a rapid attack. The combination of speed, agility, and powerful jaws allowed it to deliver fatal bites before prey could mount a defense. Fossil evidence also suggests that Carnotaurus may have had a rough, scaly skin covered with small bumps and possibly larger osteoderms, bony plates embedded in the skin. This armored texture could have provided protection against attacks from prey or rival predators, increasing its survivability in dangerous confrontations. The discovery of Carnotaurus also sheds light on the diversity of abelisaurids, the family to which it belongs. Abelisaurids were a group of theropods primarily found in the southern continents, known as Gondwana, including South America, Africa, and India. Carnotaurus is one of the best-known members of this family, demonstrating unique adaptations like its horns and reduced forelimbs. This diversity shows how different lineages of carnivorous dinosaurs evolved distinct features in response to their environments and prey. Scientists continue to study Carnotaurus's locomotion and hunting behavior using advanced technology such as computer simulations and biomechanical models. These studies support the idea that Carnotaurus was among the fastest large theropods, capable of speeds up to 30 miles per hour or more. Such speed would have allowed it to chase down swift herbivores or quickly close distance in an ambush, making it an efficient and lethal hunter. The social behavior of Carnotaurus remains a topic of debate. While no direct evidence of pack hunting exists, its horns and possible displays suggest some level of social interaction or competition between individuals. It might have been territorial, using its horns and vocalizations to defend hunting grounds or mates. Alternatively, Carnotaurus could have been a solitary predator, relying on speed and stealth rather than strength in numbers. Despite its formidable adaptations, Carnotaurus was not invincible. It lived alongside other large predators and faced competition for resources. Environmental changes during the late Cretaceous, including shifts in climate and vegetation, as well as the arrival of new dinosaur groups, likely impacted its survival. Eventually, like many Cretaceous dinosaurs, Carnotaurus went extinct by the end of the period, leaving behind a legacy of speed, power, and unique anatomy. In summary, Carnotaurus sastrae stands out as one of the most dangerous and intriguing dinosaurs ever discovered. Its combination of bull-like horns, lightweight frame, and incredible speed make it a distinctive predator in the late Cretaceous ecosystems of South America. Its hunting strategy relied on swift ambush attacks, using agility and precision rather than brute force. Carnotaurus exemplifies the incredible diversity and specialization of theropod dinosaurs, adapting in remarkable ways to survive and dominate its environment. The story of Carnotaurus reminds us that danger in the prehistoric world took many forms. From towering giants to swift hunters, dinosaurs evolved a wide range of strategies to secure their place in the ecosystem. Carnotaurus's speed and horns set it apart as a unique and terrifying predator, a true speed demon of its time. In the isolated landmass of Madagascar, During the late Cretaceous period, approximately 70 to 66 million years ago, a formidable predator roamed the forests and floodplains. This predator, known as Majungasaurus crenatissimus, was one of the most fearsome theropods to have ever existed on this island continent. Its discovery has shed light not only on its unique physical adaptations, but also on a shocking aspect of its behavior, evidence of cannibalism. This dinosaur was a slow yet powerful hunter, equipped with a bone-crushing bite and a distinct short snout, making it a true apex predator and a chilling example of survival in a challenging environment. Majungasaurus was first described scientifically in the early 20th century, but significant fossil discoveries emerged in the 1990s and 2000s from the Majunga Basin in northwestern Madagascar. These well-preserved fossils allowed paleontologists to reconstruct much of the dinosaur's anatomy and to understand its ecological role. Majungasaurus belongs to the Velociraptor family, a group of theropods primarily found in the southern continents, known for their distinctive skull shapes, short snouts, and robust builds. This dinosaur measured roughly 20 feet in length and weighed around 1 ton, making it a medium-sized predator, but one built for power rather than speed. Unlike many theropods that relied on agility and quick strikes, Majungasaurus had a relatively slow and deliberate hunting style. Its short, blunt snout was reinforced with thick bones, suggesting it could deliver strong, crushing bites capable of breaking bones. This feature is rare among theropods, which often have longer, more slender snouts for slicing flesh. Majungasaurus, however, evolved a powerful bite specialized for consuming not just soft tissue, but also bones, a trait that likely gave it a unique advantage in its environment. The skull of Majungasaurus is characterized by its high, rounded shape and numerous rough textures and bumps, indicating strong muscle attachments for jaw closure. Its teeth were blunt, curved, and spaced widely, optimized for gripping and crushing rather than slicing. This dental morphology aligns with the interpretation that Majungasaurus could process bones efficiently, extracting marrow and nutrients that other predators might leave behind. This bone-crushing ability suggests an opportunistic feeding behavior, where the dinosaur would scavenge or consume carcasses more completely than most. One of the most remarkable and disturbing discoveries related to Majungasaurus is the evidence of cannibalism. Paleontologists found Majungasaurus bones with bite marks matching the shape and size of Majungasaurus teeth. These tooth marks were found on both juvenile and adult bones, indicating that individuals of this species fed on members of their own kind. This behavior, while rare among dinosaurs, is not entirely unheard of in the animal kingdom and can be understood as a survival strategy during times of food scarcity. Cannibalism in Majungasaurus might have served several purposes. It could have been a way to recycle nutrients in a harsh environment where prey was limited or seasonal. It might also have been a display of dominance or territorial aggression, where stronger individuals attacked weaker or injured rivals. Alternatively, carcasses of fallen Majungasaurus might have been scavenged by conspecifics, taking advantage of available food sources without direct confrontation. The environment of late Cretaceous Madagascar was a mosaic of river systems, floodplains, and dry forests. It was home to a variety of herbivorous dinosaurs, including titanosaurs and other herbivorous species, which served as potential prey for Majungasaurus. In this diverse ecosystem, Majungasaurus occupied the apex predator role, competing with other carnivores for resources. Its slow but powerful build suggests it was an ambush predator, relying on stealth and strength rather than speed to overpower prey. Its limbs were strong but not built for sustained running. The robust hind legs could deliver powerful strides over short distances, allowing Majungasaurus to launch surprise attacks. Its forelimbs were small and relatively weak, consistent with other abelisarids, indicating that prey capture and killing were primarily carried out using its jaws and body strength. Majungasaurus's short snout and strong bite would have allowed it to exploit different feeding niches than other theropods. By breaking bones, it could access marrow, an energy-rich food source that requires significant force to reach. This specialization might have reduced competition with other predators by allowing Majungasaurus to consume parts of carcasses others could not. Studies using biomechanical modeling have estimated the bite force of Majungasaurus to be among the strongest of known theropods its size. This bite force was sufficient to fracture bones and crush through tough tissues, supporting the hypothesis of bone-crushing feeding behavior. Such a powerful bite, combined with a slower hunting strategy, suggests Majungasaurus might have relied on ambush or scavenging rather than long chases. Furthermore, fossil evidence from Madagascar shows that Majungasaurus lived alongside a variety of other dinosaurs and ancient reptiles, including crocodilian species and herbivores that would have posed challenges and opportunities for feeding. The presence of large herbivores provided ample prey, but seasonal fluctuations and environmental stress might have made food scarce at times, explaining the cannibalistic behavior. Majungasaurus also shows interesting features related to social or territorial interactions. Its skull has ornamental ridges and bumps, which could have been used for display or combat between individuals. These features might have been important in establishing dominance hierarchies, protecting territory, or attracting mates. The discovery of Majungasaurus has also helped paleontologists understand the diversity and distribution of abelisaurids. Madagascar's geographic isolation during the late Cretaceous led to the evolution of unique species, and Majungasaurus is one of the best examples of how isolation can shape evolutionary paths. Its adaptations to a specific ecological niche illustrate the dynamic nature of dinosaur evolution on isolated landmasses. The story of Majungasaurus challenges previous assumptions about dinosaur behavior and ecology. The evidence of cannibalism reveals a complex survival strategy in a difficult environment, while its physical adaptations show how this predator evolved to become a powerful bone crusher rather than a fast chaser. This combination of traits made Majungasaurus a formidable and dangerous dinosaur in its time. In conclusion, Majungasaurus crenatissimus was a unique and terrifying predator of late Cretaceous Madagascar. Its slow but powerful hunting style, bone-crushing bite, and evidence of cannibalism paint a picture of a dinosaur adapted to survive in a challenging environment through strength, opportunism, and perhaps ruthless behavior. The legacy of Majungasaurus continues to fascinate scientists and dinosaur enthusiasts alike, reminding us of the complexity and diversity of prehistoric life. In the vast and ancient landscapes of what is now Patagonia, Argentina, a formidable predator ruled the Cretaceous ecosystems around 90 million years ago. This dinosaur, Mapusaurus rosae, was one of the largest and most fearsome carnivores of its time. Belonging to the Carcharodontosauridae family, Mapusaurus is a close relative of the famous Giganotosaurus, yet it reveals a remarkable and terrifying aspect of dinosaur behavior, the possibility of group hunting. The discovery of multiple Mapusaurus individuals fossilized together has provided paleontologists with an extraordinary window into how some large theropods might have cooperated as pack hunters, hunting in numbers to take down massive prey. Mapusaurus was an apex predator, measuring up to 40 feet in length and weighing around 5 to 7 tons. It was one of the largest theropods known from the southern hemisphere, and its massive size alone made it a dominant force within its ecosystem. But size was not its only advantage. The discovery of a unique fossil site in Patagonia, where bones from at least 7 individuals of various ages were found together, strongly suggests complex social behavior and possibly coordinated hunting strategies, a trait rarely attributed to large theropods. This exceptional fossil site, known as the Cueva del Cerro Cartel locality, contains the remains of numerous Mapusaurus individuals preserved together alongside bones of giant sauropod dinosaurs, believed to be their prey. The association of multiple predators with multiple prey hints at a mass death event, possibly a hunting or feeding ground, where Mapusaurus may have operated as a group rather than solitary hunters. Such evidence has radically changed scientific perceptions of dinosaur hunting behavior, suggesting that some theropods used cooperative strategies to hunt. Mapusaurus had a large skull with serrated blade-like teeth designed for slicing through flesh and bone. Its jaws were powerful, but also adapted for quick, repeated bites, enabling it to inflict multiple wounds on prey. Unlike slower, bone-crushing predators, Mapusaurus relied on speed, agility, and sheer power to overwhelm prey, and its build supports the idea of an active, mobile predator capable of pursuing large herbivores. The hypothesis of group hunting in Mapusaurus is supported by several key factors. First, the fossil site with multiple individuals provides direct evidence that these dinosaurs lived or at least died together. Second, trackways from related Carcharodontosaurids suggest gregarious behavior. Third, the enormous size of the prey available, such as the Tyrannosaur sauropods, would have been difficult for a single predator to kill. Therefore, hunting in packs would allow Mapusaurus to take down these massive animals more efficiently, increasing hunting success and survival. Group hunting requires advanced social behaviors, coordination, and communication, traits that were previously assumed to be limited in large theropods. However, the Mapusaurus findings imply that some theropods may have had the neurological capacity for complex behaviors. While evidence for pack hunting in dinosaurs is still debated, Mapusaurus remains one of the strongest cases supporting this idea. Mapusaurus's anatomy further supports its role as a cooperative predator. Its long legs, strong hind limbs, and relatively lightweight body for its size suggest it was built for sustained movement and bursts of speed. These traits would be advantageous in chasing down prey or working with others to encircle and trap large herbivores. The shape of its skull and teeth indicate a predator capable of inflicting deep wounds quickly, possibly weakening prey during a prolonged hunt. The presence of juveniles and adults in the fossil assemblage indicates that Mapusaurus groups may have been family units or social packs. Such social structures would require a degree of parental care or social interaction uncommon in large predatory dinosaurs. This challenges traditional views of theropods as strictly solitary hunters and opens new possibilities for understanding dinosaur social life. Besides hunting, group living could have provided other survival benefits for Mapusaurus. Protection against rival predators, cooperative care of young, and more efficient territory defense might have contributed to the evolution of social behavior in this species. In ecosystems where large herbivores dominated, the ability to hunt in groups would have provided a significant advantage. Scientific studies comparing Mapusaurus to modern predators, such as wolves and lions, help paleontologists model how pack hunting might have functioned. Coordination between individuals to flank prey, deliver repeated bites, and protect each other during feeding could explain the survival success of these large carnivores. However, the evidence is still subject to interpretation. Some scientists argue that the fossil assemblage might represent a catastrophic event, such as a drought or flood, where multiple individuals died coincidentally in the same place, rather than evidence of social hunting. Yet, the anatomical and ecological context strongly supports social behavior hypotheses. Further research and fossil discoveries may provide more clarity. The potential for pack hunting in Mapusaurus adds a new dimension to our understanding of dinosaur behavior, revealing that these ancient creatures might have been more intelligent and socially complex than previously imagined. The story of Mapusaurus highlights the diversity of predatory strategies that dinosaurs developed during the Cretaceous period. While some theropods relied on speed and solitary ambush tactics, Mapusaurus likely embraced social cooperation to dominate its environment. This combination of size, strength, and potential teamwork made Mapusaurus one of the most dangerous dinosaurs ever discovered. In summary, Mapusaurus rosae stands as a remarkable example of death in numbers, where the power of the pack might have been as terrifying as the power of any single predator. The discovery of multiple individuals fossilized together provides compelling evidence of social behavior and cooperative hunting, setting Mapusaurus apart in the dinosaur world. As paleontologists continue to uncover more fossils and refine their theories, Mapusaurus remains a key piece of the puzzle in understanding how some of the most dangerous dinosaurs survived and thrived in the late Cretaceous ecosystems of South America. Among the many terrifying dinosaurs that ruled the prehistoric world, Therizinosaurus holds a unique place. Unlike the meat-tearing jaws of Tyrannosaurus rex or the pack-hunting ferocity of Utahraptor, Therizinosaurus didn't need teeth to strike fear. Instead, it brandished weapons unlike any other dinosaur, massive scythe-like claws stretching over a meter in length. These claws, along with its unusual body shape and mysterious behavior, have earned Therizinosaurus the title of one of the most dangerous dinosaurs ever discovered, not because of what we fully understand, but because of what we don't. Therizinosaurus was first unearthed in the late 1940s in the Nemec Formation of Mongolia, a fossil-rich site that has revealed many Cretaceous-era secrets. When paleontologists first encountered its giant claws, they assumed it belonged to a giant turtle-like reptile. It wasn't until decades later that further fossils, including parts of its skull, pelvis, and limbs, painted a clearer, more bizarre picture of this creature. Toweringly tall, possibly exceeding 10 meters, 33 feet, in length, and standing upright like a bird, Therizinosaurus had a pot-bellied torso, a long neck, and a tiny head. This strange build baffled early researchers, especially because its teeth suggested a plant-based diet. Yet, despite its classification as a herbivore or possibly an omnivore, its claws are more reminiscent of a predator or combatant. Its claws are the longest known of any land animal in history, shaped like long, curved blades that could have been used for slashing, ripping, or even climbing. Their sheer size and curvature suggest they weren't just for show or gentle foraging. They could disembowel predators, defend territory, or establish dominance. In a world of predators, this was a dinosaur that didn't run it, stood its ground, claws raised. Therizinosaurus's evolutionary lineage only adds to the intrigue. It belonged to the theropod group, the same broad group as the fearsome tyrannosaurs and the agile raptors. However, within this group, it was part of a rare branch known as Therizinosaurs, bizarre, feathered dinosaurs that walked on two legs, had long necks, and likely sported feathers. In fact, Therizinosaurus might have resembled a massive, feathered sloth-like creature with talons capable of devastating force. Some scientists believe its claws may have had multiple uses. It could have used them to pull down branches, strip leaves, or dig into tree trunks for nesting or insects. But in terms of defense, these claws would have been terrifyingly effective. A predator attempting to attack Therizinosaurus might have found itself slashed across the face, impaled through the gut, or backed off by a threat display involving those sweeping blades. Fossil evidence also suggests it lived in environments populated by apex predators like Carnotaurus, a close relative of T. Rex. That means Therizinosaurus needed serious defenses to survive. Its imposing height, bulk, and claws likely made even these top predators think twice. Its skull was small and beaked, with reduced teeth, reinforcing the herbivore theory. However, it's also possible that Therizinosaurus was an opportunistic omnivore, capable of supplementing its diet with small animals or carrion when necessary. Its long neck allowed it to browse from high vegetation, much like modern giraffes, while its wide hips and broad gut indicate it could digest fibrous plant material efficiently. Behaviorally, we can only speculate. Some paleontologists believe Therizinosaurus may have used its claws for mating displays or in intraspecific combat fights between members of the same species. This would align it more closely with animals like deer or goats today, which use their horns not just for defense, but for social hierarchy. Paleoart and reconstructions often depict Therizinosaurus as a hulking, feathered giant looming over the vegetation, claws arched, eyes wary. Its eerie combination of bird-like traits and monster-like appendages has also made it a popular figure in pop culture, from documentaries to video games and movies. Despite the lack of complete fossil remains, the bones we do have provide insights into its biomechanical potential. Studies suggest that its claws, while not as fast as those of raptors, could still deliver a tremendous amount of force due to the leverage provided by its long arms and strong shoulder muscles. Even a defensive swipe could easily cause lethal damage. One theory posits that Therizinosaurus used its claws in a defensive manner similar to how modern sloths use theirs, not necessarily to attack prey, but to make itself a target not worth attacking. Unlike sloths, however, Therizinosaurus was large, likely fast enough to maneuver, and capable of delivering a brutal counterattack. Moreover, its legs, while not built for sprinting like a Velociraptor's, were strong enough to carry its large frame, and likely allowed it to turn quickly an advantage when facing threats. Its tail, though less understood, may have been used for balance or even as an additional defensive tool. Therizinosaurus challenges our assumptions about what makes a dinosaur dangerous. Danger isn't limited to predatory behavior. The capacity to inflict harm, defend with overwhelming force, and intimidate attackers also counts. In this light, Therizinosaurus may have been one of the most effective defensive dinosaurs in history, possibly rivaling or surpassing predators in raw danger. Modern comparisons are difficult because there's truly nothing like it alive today. The blend of herbivory, enormous claws, and theropod lineage makes it a singular creature in evolutionary history. It reflects the complexity of dinosaur evolution, how a lineage that includes some of the most brutal predators can also produce such a bizarre yet deadly giant. In recent years, paleontologists have discovered more close relatives of Therizinosaurus, which help fill in the gaps. These discoveries support the idea that the family of Therizinosaurs evolved in parallel with predators, adapting not with teeth or speed, but with defensive morphology and perhaps even group behavior. We still don't know if Therizinosaurus lived in herds or family groups, but if it did, a coordinated defense using those claws could have made it nearly untouchable. Ultimately, Therizinosaurus teaches us that danger in the dinosaur world came in many forms. While it may not have hunted other dinosaurs, it was no less threatening. Towering, clawed, and armored with mystery, it stands as a reminder that in the age of giants, even plant-eaters could be monsters. When we look back across millions of years to the age of dinosaurs, the question which was the most dangerous dinosaur might seem simple, yet the answer remains elusive and complex. Through fossil evidence, anatomical studies, and the latest paleontological research, we can piece together a picture of danger, power, and ferocity in these extinct giants. But what truly defines a dinosaur as dangerous? Is it size, strength, speed, intelligence, or a combination of these traits? Even with decades of fossil discoveries, science continues to uncover new mysteries and questions, reminding us how much remains unknown. From a paleontological perspective, dangerous is a multifaceted concept. It involves physical adaptations that enabled a predator to hunt and kill effectively, such as powerful jaws, sharp teeth, agility, and protective features like horns or armor. It also includes behavioral traits like potential intelligence, social hunting strategies, and the ability to dominate an ecosystem. Danger isn't just raw power, it is the combination of anatomy, behavior, and environmental context that made a dinosaur a top predator in its time. The fossil record provides remarkable glimpses into these traits, but also poses significant limitations. Fossils are incomplete and fragmented, often leaving us with partial skeletons and limited evidence about soft tissues, behavior, and ecological interactions. Discoveries like the pack-hunting evidence in Mapusaurus or bite marks showing cannibalism in Majungasaurus offer tantalizing clues, but they also raise more questions than answers. How widespread was social hunting among theropods? Did intelligence vary significantly between species? What role did environmental pressures play in shaping these predators' behavior? Skull analysis and bite force estimations give us scientific ways to quantify danger, but they cannot capture the full picture of how these animals lived and interacted. A powerful bite doesn't guarantee hunting success without factors like speed, stealth, or cooperation. Similarly, behavioral theories based on fossil assemblages and trackways must be approached cautiously, as they rely heavily on interpretation and comparisons to modern animals, which are not perfect analogues. Moreover, new technologies like 3D scanning, biomechanical modeling, and chemical analysis of fossils continue to transform our understanding. Each new find adds layers of depth, from microscopic tooth wear, revealing diet to isotopic analysis, hinting at migration patterns. Paleontology is a constantly evolving science, one where today's established ideas may be overturned by tomorrow's discoveries. The danger these dinosaurs represented was not just in isolated traits, but in their evolutionary success across millions of years. They adapted to changing climates, competed with other species, and filled ecological niches that no other animal could. Their extinction, while marking the end of an era, also leaves behind a legacy of power and mystery that captivates the human imagination. The most dangerous dinosaurs ever discovered, whether the swift and deadly Utahraptor, the horned and agile Carnotaurus, the cannibalistic Majungasaurus, or the pack-hunting Mapusaurus, are windows into a past where survival was a daily challenge, fought with tooth and claw. Yet, these creatures are more than just dangerous predators. They are chapters in a story about adaptation, survival, and the relentless drive of life. As we continue to explore fossil sites, develop new research methods, and challenge old assumptions, we edge closer to understanding these giants not just as monsters of the past, but as complex, dynamic beings that shaped the ancient world. But science has yet to reveal all their secrets. The skulls, bones, and footprints we study are only shadows of the lives they lived, the battles they fought, and the ecosystems they ruled. This enduring mystery, combined with the sheer power and danger of these extinct giants, ensures that dinosaurs remain some of the most fascinating and awe-inspiring creatures ever to walk the earth. Their legacy reminds us that nature's greatest predators are shaped by forces beyond mere strength, by evolution, environment, and time itself. In closing, while our knowledge has grown immensely, what science still hasn't revealed about these dangerous dinosaurs is a vast frontier. Each new discovery could rewrite what we know about their hunting strategies, social lives, and survival tactics. The story of these ancient predators is far from finished, and their danger continues to challenge and inspire us, millions of years after their extinction. The skull of a dinosaur is more than just a bony structure. It is a complex, finely tuned weapon and a window into the predator's hunting capabilities, feeding strategies, and evolutionary history. By examining skull anatomy in dangerous dinosaurs, paleontologists unlock secrets of how these apex predators could dominate their ecosystems through a combination of power, precision, and adaptation. In carnivorous dinosaurs, the skull must balance two essential demands: strength and efficiency. It must be robust enough to endure the tremendous forces involved in biting and struggling prey, yet light enough to allow quick and agile movements. This delicate balance is achieved through a combination of bone architecture, muscle attachments, and specialized teeth that together form a highly effective predatory toolkit. One of the most striking features of apex predator skulls is the reinforcement of cranial bones. Many predatory dinosaurs evolved thickened and fused bones around the skull to withstand the stresses generated by biting. These reinforcements acted like a natural helmet, protecting the skull from fracturing even when biting through tough hides, bones, or during violent struggles with large prey. For example, Tyrannosaurus rex, one of the most powerful hunters to have ever lived, had remarkably thickened cranial bones with fused sutures that increased skull rigidity. This adaptation allowed T, Rex to deliver bone-crushing bites without damaging its own skull, a vital feature for an animal feeding on large herbivores like Triceratops or Hadrosaurs. The shape of the skull itself varies greatly among dangerous dinosaurs, reflecting different hunting styles and feeding behaviors. Some, like Allosaurus, possessed long, narrow skulls with blade-like teeth, perfect for slicing flesh with slashing bites. Others, such as Carnotaurus, had shorter, deeper skulls designed for delivering strong, rapid bites in ambush attacks. The robust skull of Giganotosaurus, another large predator, indicates it was capable of inflicting massive wounds, likely hunting large sauropods by targeting softer, vulnerable areas of the body. Jaw musculature plays a central role in bite force and feeding efficiency. Although soft tissues rarely fossilize, paleontologists infer muscle size and arrangement by studying muscle attachment sites on the skull. Large openings in the skull called fenestrae reduce weight while providing space for powerful muscles. The position and size of these fenestrae indicate the size of jaw muscles and, by extension, the potential bite force. In tyrannosaurids, the temporal fenestrae are notably large, suggesting they had enormous jaw muscles capable of generating bite forces estimated to exceed 8,000 pounds per square inch, strong enough to crush bone and tear through flesh with ease. This exceptional bite force likely gave T. rex an advantage over contemporaries by allowing it to access marrow and nutrient-rich bone tissues that other predators could not exploit. In contrast, smaller theropods like Velociraptor had relatively smaller jaw muscles, but their agility and sickle-shaped claws compensated for this. Velociraptors likely relied on swift, precise strikes to disable prey rather than brute force. Their skulls, though lightly built, were designed for rapid jaw closure and sharp slicing teeth to tear flesh quickly. Teeth morphology is a direct reflection of feeding strategies and dietary specialization. Serrated teeth are common in carnivorous dinosaurs, acting like a serrated knife to cut through tough muscle and connective tissue. The serrations, or denticles, increased cutting efficiency and helped predators process food quickly, reducing the time prey had to escape or fight back. In addition to serrations, teeth vary in shape and size according to their role. Some theropods had recurved teeth designed to hold onto struggling prey, preventing escape once bitten. Others had blade-like teeth optimized for slicing, while some, like Majungasaurus, had shorter, thicker teeth capable of crushing bone. This variety indicates a wide range of hunting tactics and prey preferences among dangerous dinosaurs. Skull adaptations also include specialized structures beyond bone and teeth. For example, Carnotaurus sported distinctive bull-like horns above its eyes. These horns may have been used for display, combat with rivals, or to protect the skull during predatory attacks. Similarly, some dinosaurs had reinforced snouts or reinforced jaw tips to resist twisting and shaking movements from struggling prey. The biomechanics of biting can be estimated using modern technology like 3D scanning and finite element analysis, which simulate how skulls respond to stress during biting. These biomechanical models help scientists estimate bite force and identify weak points in the skull. Such analyses have revealed that tyrannosaurids had a biting strategy that maximized force near the back of the jaw for crushing bones, while allosaurids relied more on slicing with rapid jaw closure. These biomechanical insights extend to understanding feeding behaviors. A powerful bite force allows a predator not only to kill prey, but to access marrow by breaking bones, a high-calorie resource. Predators with such abilities could survive longer on fewer kills or scavenge more effectively, providing evolutionary advantages. Comparing skull structures across dangerous species highlights how evolution tailored predators to their environments. For instance, the skull of Utahraptor, a larger relative of Velociraptor, shows a combination of strength and agility, with large sickle claws complementing a skull capable of precise, deadly bites. This contrasts with the lightly built but fast Carnotaurus, whose skull emphasizes speed and ambush predation over brute force. Fossil evidence also hints at social behavior influencing skull adaptations. In Mapusaurus, fossils of multiple individuals found together suggest possible pack hunting. In such social predators, skull adaptations might favor cooperative hunting techniques, requiring not just powerful bites but strategic use of jaws to subdue prey with teamwork. Skull morphology also reveals ecological niche partitioning, where multiple predators in the same region evolve distinct skull features to reduce competition. In late Cretaceous South America, giant predators like Giganotosaurus and Mapusaurus coexisted by specializing in different prey or hunting strategies, reflected in their skull differences. Giganotosaurus had a larger, more robust skull suited for overpowering massive prey, while Mapusaurus, with slightly lighter skull features, might have relied more on speed and group tactics. These skull differences emphasize that danger in dinosaurs was not a one-size-fits-all trait, but a diverse set of adaptations honed by millions of years of evolution. Dangerous predators came in many forms, from bone-crushing tyrannosaurids to agile pack-hunting raptors, each with skulls uniquely designed for their way of life. The study of fossilized skulls continues to evolve with technology. High-resolution CT scanning reveals internal structures like sinuses and brain cases, offering insights into sensory abilities and cognitive capacities. These data contribute to understanding how dangerous dinosaurs perceived their environment and coordinated hunting. Isotope analysis of fossil teeth helps determine diet and migration patterns, linking skull anatomy to ecological roles. Bite marks on prey fossils compared to predator teeth shapes allow reconstruction of predator-prey interactions, helping confirm feeding behaviors suggested by skull anatomy. Yet, despite all advances, many mysteries remain. The exact behavior of these predators, how they used their skulls in social interactions or fights, and how juvenile skulls developed compared to adults remain subjects of ongoing research. Every new fossil find and technological breakthrough adds to this dynamic picture of predation in the age of dinosaurs. In summary, the power behind the bite in dangerous dinosaurs is a story written in their skulls. Through detailed examination of bone structure, muscle attachments, teeth design, and biomechanical modeling, science reveals how these predators mastered the art of killing. Their skulls were not mere bones, but instruments of survival, forged by natural selection to deliver lethal bites, resist damage, and exploit every opportunity in a prehistoric world filled with danger. These evolutionary innovations in skull structure represent some of nature's most impressive engineering feats. From reinforced bones that withstand massive forces to serrated teeth perfectly designed for cutting, the anatomy of these ancient predators continues to inspire awe and deepen our understanding of life millions of years ago. The skull is more than a fossil. It is the legacy of the most dangerous dinosaurs ever discovered, a testament to their power, adaptability, and the enduring mystery of their lives. As research continues, we move closer to fully comprehending the deadly mechanics behind the bite that once ruled the ancient Earth. The senses of a predator are vital tools in the ancient struggle for survival. While much attention is given to the physical weapons of dangerous dinosaurs, their claws, teeth, and skull structure, their sensory abilities were equally critical in determining hunting success. Vision and smell, in particular, played pivotal roles in detecting, tracking, and capturing prey in complex prehistoric ecosystems. Unlike soft tissues, sensory organs rarely fossilize, but paleontologists can infer the development and function of these senses from the structure of dinosaur skulls, particularly the size and shape of eye sockets, nasal cavities, and brain case features. These clues offer fascinating insights into how dangerous dinosaurs perceived their world and honed their predatory skills. Eye sockets and vision, the window to hunting precision. The size, shape, and orientation of the orbits, the bony cavities housing the eyes, reveal much about a dinosaur's visual capabilities. Forward-facing eyes are a hallmark of predators requiring precise depth perception to judge distances accurately when stalking or attacking prey. This binocular vision allows for a three-dimensional view, essential for calculating strike distance and timing. Many theropod dinosaurs, including Tyrannosaurus rex, Velociraptor, and Utahraptor, possessed forward-facing eyes with overlapping fields of vision. Studies of T. rex skulls show large, forward-oriented orbits positioned to provide significant binocular overlap. This adaptation would have enabled T. rex to estimate distances with great accuracy, essential for delivering fatal bites or lunging strikes. In contrast, herbivorous dinosaurs generally had eyes positioned more to the sides of their heads, maximizing peripheral vision to spot predators but sacrificing binocular depth perception. This difference highlights how sensory anatomy reflects ecological roles and survival strategies. The size of the eye sockets also suggests relative visual acuity. Larger orbits could accommodate bigger eyes, which generally collect more light and provide sharper vision. Nocturnal or crepuscular hunters often have enlarged eyes to see better in low-light conditions, though evidence for nocturnality in dinosaurs remains debated. Fossilized scleral rings, bony supports inside the eye found in some dinosaur groups, provide additional clues about vision. Analysis of scleral rings in certain theropods indicates that some species may have been adapted for activity at dawn, dusk, or nighttime, potentially using their vision to hunt when other predators were less active. Olfactory bulbs and the sense of smell. Olfaction, the sense of smell, was another crucial sense for dangerous dinosaurs, especially those that hunted or scavenged over large territories. The size and complexity of the olfactory bulbs within the brain case, as revealed by endocasts, internal molds of brain cavities, serve as indicators of the animal's reliance on smell. Tyrannosaurus rex stands out for its exceptionally large olfactory bulbs, proportionally larger than those of most other theropods and even many modern carnivores. This suggests T. rex possessed an acute sense of smell, enabling it to detect prey or carrion from considerable distances. This advantage would have been vital in the vast Cretaceous landscapes where food resources could be scattered. A strong olfactory sense aids in tracking wounded or hidden prey, finding mates, and even detecting competitors or threats. It also supports scavenging behavior, allowing predators to locate carcasses before other animals. The keen sense of smell combined with formidable physical power made T. rex a versatile and dominant predator. Other theropods like Allosaurus and Abelisarids also had well-developed olfactory bulbs, though typically not as large as Tyrannosaurids. These differences hint at varying hunting strategies. Some predators might have relied more on sight and ambush tactics, while others combined vision and smell for a broader hunting approach. Integration of senses for hunting success. Vision and smell did not operate in isolation. Dangerous dinosaurs integrated multiple sensory inputs to maximize hunting efficiency. Keen eyesight allowed precise targeting and strike timing, while an acute sense of smell aided in locating prey or carrion over longer distances or dense vegetation. This sensory integration would have been especially important in competitive environments where multiple predators coexisted. Predators needed to detect prey quickly, avoid other large carnivores, and choose the most efficient hunting tactics. For example, pack hunting species like Mapusaurus may have relied on combined sensory information to coordinate attacks. Vision could guide individual strikes, while smell helped locate prey or communicate between group members through scent cues. The ability to detect subtle environmental cues such as movement, scent trails, or sounds gave predators an edge over prey that often evolved complex camouflage and evasive behaviors. This ongoing evolutionary arms race drove the refinement of sensory organs and hunting strategies. Case studies, sensory specialization in dangerous dinosaurs. Tyrannosaurus rex, The combination of large forward-facing eyes and enormous olfactory bulbs suggests T. rex was both a visual hunter capable of precise attacks and a scavenger or tracker relying on smell. Its powerful legs and jaws complemented these senses, making it a formidable apex predator. Velociraptor, despite its smaller size, Velociraptor's large eyes and well-developed olfactory regions indicate a predator relying on sharp vision and smell to hunt small to medium prey. Its agility and intelligence, combined with keen senses, likely made it an effective ambush hunter. Majungasaurus, fossil evidence, suggests a more limited binocular vision but a strong sense of smell. This dinosaur's skull shows adaptations for powerful biting and bone crushing, possibly compensating for slower speed with enhanced sensory detection of scavenging opportunities or weak prey. Carnotaurus, its relatively small eyes but large nasal cavities imply a greater reliance on olfaction. The Carnotaurus's speed and ambush tactics were supported by this acute sense of smell to detect prey or avoid larger predators. Mapusaurus, as a possible social hunter, Mapusaurus's sensory capabilities may have been tuned for group hunting, combining vision and smell for coordinated attacks on large prey herds. Evolutionary pressures shaping sensory abilities. The evolution of sensory organs in dinosaurs was driven by ecological pressures. Prey species evolved better camouflage and escape behaviors, pushing predators to develop sharper senses. Competition among predators for limited resources further accelerated this sensory refinement. Environmental factors like habitat type influenced sensory development. Forested environments favored enhanced smell and hearing to locate prey hidden by vegetation, while open plains favored acute vision for long-distance spotting. Sensory adaptations also influenced dinosaur behavior and life history. Keen senses supported complex hunting strategies, territorial behaviors, and social interactions. These sensory traits were passed down and modified through generations, shaping the diversity of dangerous dinosaurs. Modern analogues and comparative anatomy. Scientists often compare dinosaur sensory anatomy with modern animals to infer function. Birds, as living dinosaurs, provide a useful model. Many predatory birds like hawks and owls possess binocular vision and acute hearing, relying on similar sensory integration for hunting. Crocodilians, close relatives of dinosaurs, have excellent smell and vision adapted for hunting in water and on land, showing how these senses can be versatile across different environments. By studying these modern analogues, paleontologists refine hypotheses about dinosaur sensory ecology and behavior, bridging millions of years of evolutionary history. Technological advances in sensory studies. Recent advances in imaging, such as high-resolution CT scanning, enable detailed reconstructions of dinosaur brain cases, revealing olfactory bulbs, optic lobes, and other sensory centers. Finite element analysis helps model how skull features supported sensory organs and how sensory input translated into behavior. Stable isotope and microwear analysis on teeth complement sensory studies by providing data on diet and hunting methods linked indirectly to sensory reliance. Limitations and ongoing questions. Despite progress, many questions remain about the sensory world of dangerous dinosaurs. Soft tissues like eyes, nerves, and sensory cells do not fossilize, limiting direct evidence. Behavioral interpretations rely on anatomical proxies, which may not capture the full complexity of sensory processing. The degree of nocturnality or diurnality in many species is still debated, affecting conclusions about vision and smell. Future fossil discoveries and technological innovations promise to shed more light on these mysteries, deepening our understanding of dinosaur sensory biology. Summary. The senses of vision and smell were fundamental to the hunting efficiency of dangerous dinosaurs. Fossil skulls reveal that forward-facing eyes with binocular vision allowed precise depth perception and accurate strikes, while enlarged olfactory bulbs supported an exceptional sense of smell for tracking prey and scavenging. These sensory adaptations were finely tuned through evolution, enabling predators like Tyrannosaurus rex, Velociraptor, and Mapusaurus to dominate their environments. The integration of multiple senses allowed these ancient hunters to detect, pursue, and capture prey in competitive, dynamic ecosystems. The study of dinosaur sensory biology offers not only insights into their lives, but also a window into the evolutionary pressures shaping predator-prey relationships over millions of years. As science continues to advance, the sensory world of these extinct giants becomes clearer, revealing the remarkable strategies behind their power and danger. The idea that some large theropod dinosaurs may have engaged in pack behavior or cooperative hunting has long fascinated paleontologists and dinosaur enthusiasts alike. The notion of these prehistoric giants working together to bring down large prey conjures dramatic scenes reminiscent of modern wolves or lions. Yet, understanding social behavior in extinct animals, especially dinosaurs, presents complex challenges. It requires careful interpretation of fossil evidence, combined with comparisons to living animals and cautious scientific inference. This section explores the current theories surrounding pack behavior in large theropods, examining fossil clues, modern analogues, ongoing debates, and what such behavior might have meant for hunting strategies and predator-prey dynamics during the age of dinosaurs. Fossil evidence, clues from trackways and bone beds. One of the primary sources of evidence for social behavior in dinosaurs comes from fossilized trackways and bone beds containing multiple individuals of the same species found together. Trackways, or fossilized footprints, sometimes show parallel or closely grouped prints of multiple theropods moving in the same direction, interpreted by some researchers as indicative of group movement or hunting parties. Bone beds with multiple theropods of various ages, juveniles and adults found together, suggest potential social groupings or at least repeated use of the same area. The famous Mapusaurus bone bed in Argentina, containing remains of several individuals, sparked particular interest. Some paleontologists suggest these dinosaurs may have hunted cooperatively, taking down large herbivorous prey like Tyrannosaurs. However, interpreting these assemblages is complex. Multiple individuals could have died together due to environmental events, water transport, or predator traps rather than cooperative behavior. The fossil record often provides snapshots rather than continuous behavioral records, making definitive conclusions challenging. Modern analogues, wolves, lions, and beyond. To better understand potential dinosaur pack behavior, scientists look to living social predators. Wolves are the classic example of cooperative hunters using coordinated tactics to chase and exhaust prey. Their social structures involve packs with hierarchies and roles, supporting hunting success and survival. Lions also hunt in prides, often collaborating to ambush and isolate prey, using tactics that benefit from group strength and coordination. Other modern carnivores, such as African wild dogs and hyenas, display pack or clan hunting behavior, relying on teamwork to increase kill rates and defend territory. These modern animals provide models for how large theropods might have organized social hunting, though differences in physiology, ecology, and brain function caution against direct one-to-one comparisons. Challenges and controversies in interpreting dinosaur social behavior. One major challenge in interpreting dinosaur social behavior is the absence of direct observational evidence. Behaviors rarely fossilize, leaving researchers to infer actions from indirect signs like fossil distribution, anatomy, and environment. Some paleontologists argue that large theropods were primarily solitary hunters, like modern tigers or crocodilians. Solitary hunting is common in large apex predators, supported by anatomical evidence such as skull strength adapted for quick killing strikes rather than prolonged group chases. Skeptics highlight that fossil boneheads may represent catastrophic death events rather than social groups. Trackways may reflect coincidental overlapping paths rather than intentional group movement. Debates also focus on whether cooperative hunting requiring communication, role differentiation, and social bonding was possible given the neurological and cognitive capacities of theropods. While some evidence points to intelligence in species like Velociraptor and Utahraptor, the degree of social complexity remains uncertain. Specific case studies beyond Mapusaurus. Beyond Mapusaurus, other large theropods show tantalizing clues that may support some level of social behavior. Allosaurus. Several fossil sites contain multiple Allosaurus individuals together. Some paleontologists suggest possible pack living or at least loose social aggregations. However, definitive evidence of cooperative hunting remains lacking. Deinonychus and Velociraptor, these smaller but formidable predators, show anatomical features suggestive of agility and intelligence. Trackways and fossil finds indicate they may have hunted in groups or family units, using coordinated ambush tactics on larger prey. Carnotaurus, like Mapusaurus, it was a large apex predator from South America and Africa. Limited evidence exists about social behavior, but its ecological niche suggests potential competition or cooperation. How pack behavior could have influenced hunting strategies. If large theropods did engage in pack or group hunting, this would have had profound implications for their hunting strategies and ecology. Cooperative hunting could allow predators to take down larger, more dangerous prey than solitary hunters could manage, improving food intake efficiency. Hunting in groups may also reduce injury risk, distribute effort, and increase kill success rates. Pack behavior might have influenced territoriality, mating systems, and social hierarchies, creating complex group dynamics. Scent marking, vocalizations, and visual displays could have played roles in coordination and social bonding. Predator-prey dynamics would shift accordingly, with prey species evolving new defenses or avoidance tactics against group hunters. This arms race could drive rapid evolutionary changes in both predator and prey species. Conclusion: current understanding and future directions. The question of pack behavior in large theropods remains open. Fossil evidence provides intriguing hints, but also raises doubts and alternative explanations. Modern analogues help frame hypotheses, but cannot fully resolve uncertainties. Ongoing discoveries and advances in technology, such as improved imaging and biomechanical modeling, may soon reveal more about dinosaur social life. Understanding pack behavior offers insight not just into hunting tactics, but into the social complexity and intelligence of these ancient predators. As science progresses, the mysterious behaviors of dinosaurs like Mapusaurus, Allosaurus, and Velociraptor continue to inspire research, bridging the past with the present to illuminate the rich tapestry of prehistoric life. The fossil record offers not only snapshots of anatomy, but also windows into the lives and struggles of ancient animals. Among the most revealing evidence are injuries preserved on fossilized bones and skulls, particularly those showing signs of healing. These traces provide a unique glimpse into the behavior, social interactions, and resilience of some of the most dangerous dinosaurs ever discovered. This section explores how healed wounds and bite marks on fossil skulls reveal aggressive encounters, possible causes such as territorial disputes or dominance battles, and what they tell us about social structures, survival, and care among large theropod predators. Healed injuries on dinosaur skulls, what they reveal. One of the most compelling lines of evidence for intraspecies conflict among large theropods comes from fossil skulls bearing healed injuries. These wounds include punctures, fractures, and bite marks that show signs of biological repair, indicating the animals survived the encounter. Fossil specimens with healed injuries demonstrate that these dinosaurs frequently engaged in violent interactions, likely with rivals of their own species. Such injuries may have resulted from competition over territory, mates, or dominance hierarchies, mirroring behaviors seen in modern predators. For example, Several Allosaurus skulls show deep bite marks on the snout and jaws, some of which have partially healed. Similarly, Tyrannosaurus rex skulls display fractures and puncture wounds consistent with bites from other tyrannosaurs, with evidence of bone regrowth and remodeling. These healed wounds tell a story of repeated conflict and survival, showing that these predators were not only dangerous to their prey, but also engaged in fierce battles with one another. Possible causes of injuries, territorial disputes, and dominance battles. Territorial disputes are a common cause of injury in modern apex predators. Defending a hunting ground or nesting area from rivals ensures access to food and reproductive opportunities. It is likely that large theropods engaged in similar behaviors, aggressively protecting prime territories. Dominance battles may have occurred to establish social hierarchies within populations. These contests could involve displays of strength, vocalizations, and sometimes physical combat. Bite wounds on the skull and body would be common outcomes of such confrontations. Competition for mates is another potential driver of conflict. During breeding seasons, males might have fought to secure females or maintain harems, resulting in injuries. The nature and placement of wounds may indicate ritualized combat or more brutal encounters. Clues to social structure and behavior. The presence of healed injuries suggests that some degree of social interaction occurred among dangerous theropods. The fact that individuals survived these wounds implies they endured prolonged periods of recovery, raising questions about their ability to hunt, defend themselves, and possibly receive care. In species where healed injuries are common, social hierarchies or territorial boundaries may have been well established, with repeated encounters among individuals. The pattern and distribution of wounds can provide clues about common targets during fights, such as the head or neck. These findings also raise the possibility that some theropods engaged in less solitary lifestyles than previously thought, potentially forming loose social groups or family units where injured members could survive despite impairments. Resilience and survival after injury. Surviving severe injuries requires considerable resilience. Fossil evidence shows that many large theropods endured broken bones and bite wounds, continuing to live and grow after their injuries. Bone remodeling around wounds indicates active healing processes similar to modern reptiles and birds. Some fossils even suggest partial recovery of damaged sensory structures, such as eye sockets or jaw function, enabling continued hunting or scavenging. This resilience hints at robust immune systems and adaptive behaviors to cope with injury. Survival after injuries might have been facilitated by behavioral changes such as reduced aggression, increased caution, or scavenging instead of active hunting. Injured individuals may have relied more on ambush tactics or opportunistic feeding. Potential evidence of care within groups. One of the most intriguing questions arising from healed injuries is whether some theropods cared for injured group members. While direct evidence is lacking, some paleontologists speculate that in social species, injured individuals may have received protection or assistance. In modern social predators like wolves, injured pack members can survive thanks to food sharing and social support. If similar behaviors existed in theropods, this would suggest complex social bonds and communication. However, this idea remains speculative, as fossil evidence cannot yet conclusively demonstrate caregiving. Future discoveries of fossils showing healed injuries alongside evidence of social grouping could shed light on this possibility. Case studies, examples of fossil skull injuries. Tyrannosaurus rex. Multiple skull specimens show puncture wounds consistent with bites from other tyrannosaurs. Healed fractures indicate survival after violent encounters. Some scientists propose these were territorial or mating fights. Allosaurus fragilis, bite marks on the snout and jaws. Some partially healed suggest frequent intraspecific aggression. Allosaurus was a dominant predator of the late Jurassic, likely competing intensely for resources. Ceratosaurus, fossils reveal healed lesions and broken bones, indicating physical conflict. Their robust skulls may have helped absorb impacts during fights. Dromaeosaurids, raptors, though smaller, fossils of Velociraptor and Utahraptor show bite wounds and healed fractures, supporting aggressive encounters possibly linked to social hierarchy or territorial disputes. Implications for paleontology and dinosaur behavior. The study of injuries and healing in fossil skulls extends beyond documenting physical trauma. It enriches understanding of dinosaur behavior, social dynamics, and evolutionary adaptations. Knowing that these predators engaged in violent interactions with rivals paints a fuller picture of their ecology and life history. It highlights the pressures shaping anatomy, such as reinforced skulls and robust jaws, adapted to survive combat. Additionally, these findings inform biomechanical models of biting and fighting, refining interpretations of fossil damage. They also encourage more nuanced views of dinosaur social complexity, limitations, and future research directions. While healed injuries offer valuable insights, there are limitations. Fossilization bias means only certain injuries preserve well, and distinguishing between wounds caused by rivals, prey, or environmental accidents can be difficult. Future research combining fossil evidence with modern imaging techniques, biomechanical analysis, and comparisons to living archosaurs, birds, and crocodilians may improve interpretations. Finding more fossils with documented healing, ideally alongside evidence of social grouping, could clarify the extent of social behavior and care in these dangerous dinosaurs. The fossil record captures more than the remains of individual animals. It documents the unfolding of an evolutionary arms race, a prolonged and dynamic interplay between predator and prey that shaped skull adaptations on both sides. In this continuous struggle, predators evolved more powerful bites, sharper teeth, and specialized skulls, while prey species developed defensive skull features such as thickened domes, horns, and protective armor. This mutual pressure to survive transformed the very anatomy of some of the most dangerous and well-defended creatures ever to walk the earth. Among the predators, skull evolution focused on maximizing offensive capabilities. Traits like deep-set jaws, robust muscle attachment sites, and sharp serrated teeth evolved in response to increasingly challenging prey. Theropods such as Tyrannosaurus rex developed one of the strongest bite forces of any terrestrial animal, capable of crushing bone. The structural integrity of its skull, with interlocking bones and reinforced nasal structures, allowed it to deliver devastating bites without compromising its own anatomy. Simultaneously, prey species evolved defensive mechanisms. Fossil skulls of ceratopsians like Triceratops display elaborate frills and forward-pointing horns. Initially considered ornamental, these features are now thought to have provided active defense against predators. Puncture wounds on Triceratops frills, matched to the tooth spacing of tyrannosaurs, suggest violent interactions. The thickened skulls of pachycephalosaurs, with their dome-like cranial structures, may have served to deflect or absorb blows from both predators and rivals. Ankylosaurs present one of the most remarkable cases of cranial defense. Their low-slung, heavily armored skulls were embedded with bony plates and knobs. Coupled with their tail clubs, these dinosaurs were built like tanks. Fossilized skulls of ankylosaurs sometimes show healed bite marks, indicating they survived encounters with predators and that their skull adaptations were effective in deterring or surviving attacks. The evidence for this arms race also lies in trace fossils, bitten bones, healed wounds, and scarred frills. These interactions provide rare snapshots of predator-prey encounters. One such fossil shows a Triceratops frill with a circular bite mark that matches a Tyrannosaur's tooth pattern, with clear signs of healing. This indicates the Triceratops not only survived but likely repelled its attacker. Some hadrosaurs, often considered more vulnerable, also show skull adaptations. Their elongated snouts and cranial crests may have played roles in social signaling or acoustic communication, but there's also speculation that their wide fields of vision and spatial awareness help them evade predators. The evolution of crests and skull ridges may have had multifaceted purposes beyond defense, but even passive adaptations like these contributed to survival. This dynamic coevolution was not static. As predators grew larger and more lethal, prey species responded with tougher skulls and more elaborate defenses. Ecosystems became shaped by this interplay. In regions where apex predators thrived, prey species often display more robust or unusual skull morphologies. Where predators were smaller or less specialized, prey animals were generally less armored. These evolutionary adaptations reflect broader environmental and ecological shifts. During the late Cretaceous, for instance, the rise of large tyrannosaurids coincided with the diversification of horned dinosaurs and armored species. The balance of power between predator and prey remained in flux, as each adaptation by one side prompted a counter-adaptation by the other. Further research into microscopic bone structures, biomechanics, and comparative anatomy continues to shed light on this evolutionary arms race. Modern imaging technologies allow paleontologists to estimate bite forces, stress resistance in skull bones, and even potential muscle structure in extinct animals. The skulls of both predators and prey tell stories not only of survival, but of an ongoing war waged through evolution. Each puncture, ridge, and fracture adds a new layer to our understanding of how dinosaurs interacted with one another and with their environments. It is through these adaptations, offensive and defensive, that the true danger and resilience of these ancient species are revealed.